Hello, today we're continuing with our GCSE Physics Revision series looking at the life cycle of stars. Last time we considered the Big Bang. The resulting matter that came out of the Big Bang was principally hydrogen. That was about the only element that was formed at the Big Bang. There were some others, but they don't really matter. So the idea is that the universe is filled at the time of the Big Bang with hydrogen atoms, or very shortly after the Big Bang, to be strict about it. Now, gravity is a force that will pull any masses together. The bigger the mass, the greater the gravitational attraction. So where you have a whole range, billions and billions and billions of hydrogen atoms, the idea is that gravity will gradually cause them to pull together. And as they pull together, eventually you get a sort of a loose grouping of hydrogen atoms. And that is called a protostar. Now, when we did mechanics, we spoke about gravitational potential energy. For example, we said that if you hold a book up above the floor, it will have gravitational potential energy. You remember we said it was mgh, the mass of the book times gravity times the height above the floor. But if you drop it, it loses gravitational potential energy and it gains kinetic energy. We don't lose any energy overall, but the energy changes from potential to kinetic and it hits the floor with a thump. Well, exactly the same thing is happening in these stars. As the hydrogen atoms are falling in, they are losing gravitational potential energy, but that energy is now being converted into heat. So consequently, this protostar is getting hotter. So, gravitational potential energy is converted into heat, and that, of course, will mean that the temperature will rise. And it will rise to, in the centre of this protostar at any rate, several million degrees. And if that happens, then as we've seen before, you enter the state of matter called a plasma. A plasma is where the gas gets so hot that the electrons have enough energy to escape from the atoms, and you're simply left with the positively charged nuclei. Now, hydrogen is the lightest element of all. It has one proton in the middle and it has one electron orbiting. If that electron disappears, if you give it enough energy to kick it out, what are you left with? A proton. So consequently, the protostar is nothing more than a big ball of protons. And at 10 million degrees in the centre of that star, that is hot enough for fusion to take place. Now, we covered fusion when we did nuclear fusion. And it's exactly what happens inside a star. In essence, inside a star, hydrogen is being converted into helium. That's all that really happens for the bulk of the star's life. And just a reminder of how that works, a proton in the star is converted into a neutron plus a positron plus a neutrino. And that is stage one of the process. So now you've got protons being converted into neutrons. You can take two of the protons that were there anyway, plus two of the neutrons that you've manufactured. And from those you can form a helium nucleus, which has two protons and two neutrons, plus energy. And the reason you get energy, we explained, was that if you were to measure the mass of the two protons and the two neutrons, you would find that would be just slightly greater than the mass of the helium atom. There is what's called a mass deficit. This is bigger than this. We've lost some mass. Where has the mass gone? The mass has been converted to energy under the formula E equals mc squared. C, I remind you, is 3 times 10 to the 8th meters per second. It's the speed of light. So c squared is a massive number, 9 times 10 to the 16. So a small mass defect is converted into a large energy because you're multiplying that small number by this massive number. And this energy is, of course, what the star, or in our case, our sun, pumps out in the form of heat and light and all the radiation that comes from it. That's essentially the source. So this is essentially all that happens inside a star. It's a two-stage process. I should have said that's stage 2. So stage 1 is you need to take some of your protons and convert them into neutrons. You also get positrons, which of course will collide with the electrons that were stripped off the hydrogen atoms, and they will annihilate and produce more gamma rays. And the neutrinos, which, as I say, fly out from the sun at the rate of billions per second, and they pass straight through the Earth, they pass straight through you, because they barely ever interact with anything, so you don't notice them. So stage 1 is simply converting protons to neutrons. Stage 2 is to take 2 protons and 2 neutrons and fuse them together, because you've got these very high temperatures in the middle of the sun that enable you to do that, and that produces helium plus the energy, and the energy is what makes the sun shine. Now you'll recall that the way we got into this, the way we formed our protostar, was through what is essentially gravitational collapse. Gravity was pulling all these hydrogen atoms together. And as the hydrogen atoms fell in, they lost potential energy, gravitational potential energy, and that was transferred into heat. So why doesn't the star continue to collapse through gravity? Well, the answer is that in the core, we've now got nuclear fusion reactions happening, and they are creating a pressure which goes outwards. And for the life of the star, the nuclear fusion at the core produces an outward pressure which exactly matches the gravitational forces which are trying to pull the outside of the star inwards. And so you've got a balance, a nice balance between the gravitational collapse and the nuclear fusion pressure, which keeps the star at broadly the right size for the whole of its life. The temperature at the core of our sun is of the order of 14 million degrees centigrade. The temperature at the edge is probably only something like 6,000 degrees centigrade. So the sun's surface is a lot cooler, and there isn't enough energy in the outer parts for fusion to take place. You remember, fusion needs millions of degrees centigrade. No fusion can happen here. Fusion is just happening in the core. So it's the core where protons are being converted into neutrons, and where 2 protons and 2 neutrons are being converted into helium. And that process will carry on in the sun for 10 billion years. In fact, we are halfway through. The sun has been shining for about 5 billion years, so it's got about another 5 billion years to go. Why does it take so long? Well, actually, it takes so long because this process of converting protons to neutrons is caused by what is called the weak force. It doesn't happen very often. Now, it obviously happens enough that the sun can shine, but actually, of course, there is a huge number of protons in the sun. If they were all converted to neutrons in hardly any time at all, the sun would burn out very quickly, and we would never have had a chance to establish life on Earth. It is precisely because this process is a weak interaction, and that protons take their time to be converted into neutrons, that the sun is able to shine for 10 billion years, because there will be still protons in the core that have not yet been converted to neutrons for another 5 billion years. And all the time the sun's factory is doing this, converting protons into neutrons and then putting neutrons and protons together to make helium. It is called a main sequence star. It's just what stars do for the bulk of their life. And of course, while they're doing that, you have the opportunity for, here's the sun, you have the opportunity for planets to form around the Sun, and one of those planets might be called, well, let's call it Earth. And for 5 billion years, there's been the opportunity on Earth to use the sunlight and the sun energy to create life. And life may well continue on Earth for almost another 5 billion years until the Sun eventually goes into another stage. So what happens? Well, remember that it's at the core, where it is hottest, that the protons are being converted into neutrons and then combined to form helium. Now there will come a point where the protons in the core have been used up, and that core is now pretty much full of helium. So no further fusion can take place because there aren't any more protons and neutrons to do the fusion. When that happens, fusion stops. But gravity still is working. Remember, gravity has so far been held at bay by the pressures from the fusion reactions. When the fusion reaction stops, then there is now nothing to stop the gravitational collapse. So all the gas that is in the, as it were, outer edges of the Sun, that's much cooler, starts to collapse onto a core that is 14 million degrees centigrade. And that causes a bit of a reaction. What you find is two things happen. Firstly, the core comes under great pressure and therefore starts to shrink and get hotter and hotter. So the temperature of the core now goes even higher, but the gases around it expand massively and the star becomes a red giant. Red because it looks red in the sky, and it's red because now the outer edges are much cooler, because obviously they are now further away. The inner core is much hotter, the outer edges are much cooler. But because the inner core is now much hotter, more fusion can take place. Remember that inside the core we've got helium. That's all we were able to manufacture at the temperatures at the core of the Sun. But now that the temperatures have got hotter, we can start making atoms that are higher than helium. We can, for example, start making carbon and oxygen and nitrogen, elements that are essential for life. And in fact, depending on how hot it is at the centre, you can make atoms all the way up to iron, but no further. Iron is the limit at this stage of the process. Some stars are not hot enough to get all the way up to iron. You need hotter and hotter temperatures for larger and larger atoms. But if you do, then what you end up with a star that's got a molten, as it were, centre of iron where all the elements have been fused to produce iron. And then surrounding that iron core will be layers of elements, progressively smaller. So somewhere in here we're going to have oxygen, and then maybe in the next layer we're going to have nitrogen, and maybe in the next layer after that we'll have carbon, and then in an outer layer we're going to have helium, and then in the furthest layer of all, hydrogen. So the idea is as you progressively move in towards the star, it gets hotter and hotter and hotter. The hotter it gets, the bigger and the more massive the atoms that can be produced, until you get to the centre where the most massive atom that you can produce in this system is made, and that's iron. When you've got a core of iron, no further fusion can take place. That part of the process comes to an end. So now what happens? Well, gravity is still working. It has been held at bay again by all these fusion processes that have been creating all these elements. That has been producing pressure, which has been holding the gravity at bay. But now the fusion stops because there's nowhere else to go. And so gravity happens again. So let's just have a look. We've now got our star with all our elements in concentric circles, as it were. And we've got the hydrogen of the red giant around the star. And now gravity is on its own because all the nuclear fusion has finished. So gravity pulls the hydrogen of the outer part of the star into the centre. So you've got these gases from the outside falling into a monumentally high temperature. And the result of that is the most cataclysmic of all explosions. And that's called a supernova. And when a supernova happens, one star exploding in this way can be brighter than an entire galaxy that it forms a part of. And remember, a galaxy probably has about 100 billion stars in it. So one star shines brighter in those short amount of time that the supernova happens, brighter than 100 billion other stars that are all going through their main sequence. And the amount of energy in here is colossal, huge amounts. And it can take the elements that were formed in these concentric circles up to iron, and it can now produce all the other elements that are heavier than iron, right the way up to uranium and beyond. So any elements that are heavier than iron can only have been formed when they were part of a massive explosion in a supernova. Now think about this. Here is my wedding ring. It's a gold wedding ring, so it's made of gold. Where did that gold come from? There is only one place that gold could ever have come from, and that is from a supernova explosion. At some point in the past, before our sun was formed, so more than 5 billion years ago, somewhere in space, a star exploded with the most cataclysmic force that this gold was formed. The whole thing exploded and the gold was thrown into space, and eventually, as a result of gravity, the whole thing coalesced into a planet called Earth. Somebody mined it, somebody shaped it, and somebody sold it to me. And there's the ring. That ring was once in a supernova. Now, this is not the fate of all stars. Our own sun, for example, is probably not big enough. You have to be pretty big to do this. Our sun is probably not big enough. So what will happen is that after the red giant stage, what you will probably find is that the core of our sun will become what's known as a white dwarf. The core is dwarf. The core becomes hot and dense, but eventually it cools until it no emits emits light, in which case it becomes a black dwarf and you can no longer see it. The outer layers simply go off as dust and hydrogen into space, and they may form what are called planetary nebula, but of course they become a new store of dust and hydrogen that at some point in the future will coalesce as a result of all the gravitational attraction, and they will become a new star. But it's the bigger stars where the core is very hot, and as the outer layers collapse onto the core, you get the massive explosion that produces the elements that are above iron in the periodic table. That explosion will throw all of those elements that have been produced into space. So you've now got a wide range of elements that are essentially splattered all over space, and gravity, that is always lurking, will be waiting to start to pull them all together again. Mainly into stars, but in some cases they may be formed into something that never quite make the size of stars. They might be planets, and those planets will have some elements in them that had been formed during the supernova. But the core of the supernova, that really dense, hot place, that remains. And what happens to it depends again on the size of the star. Gravity is still working, and there's no fusion any longer to stop it. And what will happen is that the enormous energy associated with the gravity will pull the star down to a small size where there are no more any atoms. Indeed, there aren't even any protons. Protons have been squashed with electrons to form neutrons. All you have here is neutrons. And the neutrons are packed, no longer in atoms, but just packed side by side, densely packed neutrons. That's called a neutron star. If you were to pick up 1 teaspoonful of neutron star material, it would weigh 500 million tons. I'll say that again. If you pick up neutron star material as if you were picking up sugar from a sugar bowl with a teaspoon, that would weigh 500 million tons. That's how densely packed the material is in a neutron star. And the reason it stops is that the forces between the neutrons are sufficient to stop the gravity from collapsing the star any further. But sometimes the star is so big that even the forces that are keeping the neutrons apart cannot withstand the effects of gravity. And so gravity pushes the star, which gets smaller and smaller and smaller. And what's going to stop it? If you say at some point, well, it doesn't go any smaller, you've got to say, well, what force do we know that would stop it from happening? And there isn't one. Consequently, that star will not stop contracting until it gets to what we call a singularity, a point. And when that happens, you've created a black hole. That is now infinitely dense, and nothing can escape from it. The gravitational force is so intense, nothing, not even light, can escape. And that's why we call it a black hole, because we can't see it. So just a reminder, at the end of a star's life, there are 3 choices. If it's a small star, possibly one like our own sun, its core will become a white dwarf and eventually a black dwarf, obviously long before this life on Earth has ceased to exist. The outer layers of the sun, will just become dust and hydrogen, and that will produce a source for a new star in due course. If the star is much heavier than the sun, then it will eventually become a supernova. When it does, huge numbers of elements are produced in the massive energy explosion. They get splattered off into space, where once again they become a source of a new star. The inner core, however, has 2 roots. It will be contracted through gravity, and it rather depends on how big it is. If it's not that big, then eventually the neutrons and the forces between the neutrons will stop any further gravitational collapse, and you end up with a neutron star. If the gravity is too strong for the neutrons, then the collapse just carries on until eventually that whole core has been compressed to a point, and that is the black hole.